Okay, so the workshop is now recorded, so we can officially start. Hello, everyone. Welcome to the quantum computing workshop, QNickel16, which is an intermediate level workshop based on the educational materials developed by QWord. This workshop is organized by one of the QWord's Q cousins in Poland. It's called QPoland. And formally, it's also organized by the Quantum AI Foundation, which is a non-profit organization founded and led by me, registered here in Poland, in Warsaw. And it formally supports our QPoland events. This is a follow-up workshop. So as some of you know, last week we had an introductory level workshop, Q Bronze, and I guess that probably some of you have also participated in some of our previous Q Bronze or Q Silver workshops organized by Q Poland in the recent years. Just a few words about the organization. So we'll have 5 days of classes, starting at 7 p.m. Warsaw time every day. So as you can maybe see or recognize, I'm currently in Warsaw. I just wanted to show you in the background the Warsaw city center. So this is a Warsaw Tower just behind me. It's happened that I'm just attending a conference now in one of the hotels in Warsaw. But our instructor is from Krakow, Alex Linden. I guess that Alex is in Krakow, but maybe she can later tell you where exactly she is based. We also have a few great mentors supporting us, Martyna, Justyna, Amrit, Maya, and Mateusz. And actually, Rafał joined us today. Rafał helped us in setting up our Quantum bot on Discord. So Quantum bot will send you some reminders about the lectures, the workshops. Do we have some of our mentors now on Zoom? Or Alex? Maybe Alex, because Alex, you will have opportunity to introduce yourself later. But I just wanted to ask the mentors maybe for a quick introduction if they are with us. If not, then they have already introduced themselves on Discord. So feel free to reach them out and contact them if you have any questions. So on our Discord, we have some dedicated channels, dedicated thematic channels. So please do remember to ask your questions in the appropriate channel, thematically relevant to the topic of your question. We would also like to thank Agnieszka Wolska, who prepared graphics, banners, promotional materials for us. As I said, the materials on which this workshop is based were developed by QWord, and they're called QNickel. All the lectures will be held on Zoom, but the communication with mentors and questions should be asked on Discord. Maybe beside the questions directly addressed to the instructor during the lecture, because it might be more convenient to ask Alex directly here on Zoom on the chat, or maybe she will allow you to unmute as well. One important thing is that if you want, you can receive a certificate after the workshop. So in order to do it, you need to do some homeworks, and you need to get at least 50% of points for homeworks, for each of the homeworks, and at least 70% of general points, so from all the homeworks altogether. And there will be 5 quizzes and 3 assignments. They will be in Canvas, so just after this lecture, this introductory lecture, I will send you invitations to Canvas, so please check your mailbox. The invitations will be sent to the email addresses that you provided during the registration. And the first set of quizzes will be available later today. I think they should be available at 10 p.m. Warsaw time, so in about 3 hours from now. The last one should be made available on Friday, just after the last lecture. And then you will have 7 days to complete all the quizzes and assignments. In case of quizzes, you will have 3 attempts, and only the highest score will count. In case of assignments, which are just some programming exercises that you will need to complete in Jupyter notebooks, you will have 15 attempts. So the reason is that this is the first workshop in which um, we experiment with this programming assignments, and there is the auto grader enabled, and we are not sure how exactly it will work. So we expect and we hope that there will be no issues, but we expect that there might be some technical issues for which we already apologize in advance. So that's why you'll have 15 attempts to submit your Jupyter notebooks, and we'll see. As I said, this is the first time in which we experiment with this programming assignments. And as I said, the deadline to complete everything is October 18th, so just exactly 7 days after the last lecture. And another important thing is that you please remember about updating your names, full names, first and last name, and email addresses in Canvas. Once you receive the invitation, please do it as soon as you can, because the names that you have in Canvas will be later printed on the certificates, if you get them, of course. And the email addresses that you provide in Canvas will be also the email addresses to which we'll send the certificates. Okay. Um, all right. So maybe just a few words about QWord. I believe that at least some of you, or maybe even most of you, have heard about QWord. So it is an international organization aiming to build the open global ecosystem for quantum technologies. And we collaborate together globally and act locally. We organize different educational events like the workshops to our local communities in our countries. As for now, we have the so-called Q cousins, our local groups, entangled Q cousins in more than 30 countries worldwide, and we are still growing and expanding our network. So if you are from a country in which we still do not have a Q cousin, you can think about organizing a similar local group in your country and organize later similar educational events for your communities at your university or in a even wider area. You can, in order to stay up to date, feel free to follow our Facebook profiles, Twitter X profiles. You can join Keywords Discord. You can follow Keywords profile on LinkedIn or subscribe to YouTube channel. There are a variety of projects like workshops starting from the introductory level, which is Q Bronze. Then there are intermediate level workshops like Q Silver and Q Nickel. So this Q Nickel workshop is an intermediate level workshop. And there are also some self-study materials that are, some of them are already available, some of them will be released soon. So these materials are prepared by our Q Education department. We also have a Q Research department in which we organize online research internships. The project is called Q Intern. So researchers from all over the world can submit their project ideas, and then students from all over the world can apply, and they are matched by Keyword, and they can collaborate together on their research projects. Yeah, we also organize some longer massive open online courses like Q Course. So eventually, we would like to prepare educational materials for the complete university curriculum, like full undergraduate or graduate studies in quantum computing. So that's the long-term goal. In QPoland, our group is already quite strong. So we also have our Facebook group, fan page, profiles on LinkedIn, X. We have our Discord. We have our mailing list. You can also subscribe to our monthly newsletter. So once per month, we release a newsletter. We just try to gather all the important news from the quantum world, and then and also announce some upcoming events. And you can join us if you want, and you can stay up to date. You can follow our profiles. So I will later share this slide, so you'll have access to all these links. And just last but not least, just a few words about Quantum AI Foundation. This is a legal body behind QPoland. It's a non-profit organization that I founded a few years ago in order to support education, research, and collaboration in new technologies, especially quantum computing and AI, but also other fields of science. If you like our workshops, you can donate, but we also encourage you to donate to help us raise funds to support the victims of the recent floodings in Poland, in southern Poland. That's all from my side. If you have any questions about the organization of the workshop, I will be happy to answer, and later I will give voice to Alex, who will be our instructor during the next 5 days. Let me check on our chat if there are any questions. Uh, okay, there was some remarks about the sound, so I hope that it's better. Uh, Regarding submitting the homeworks, yes, we'll send you invitations to Canvas, as I said, and you should join the Canvas. You should update your name and your email address, and then you'll have access to the homeworks. But actually, I think that the access to the first homework will be after 10 p.m. today. But you can just check the Canvas earlier to see how it is organized and so on. Regarding the question, so uh, by default, when there are lectures like now, you can ask your questions on chat, and I think that Alex will later also explain how she would like to receive your questions during her lectures. But after the lectures, please ask your questions on Discord. There are dedicated thematic channels on Discord, and yeah. Um, will there be lecture notes that we can refer to during assignments? We'll share the recordings. Hopefully, we'll share the recordings. I'm not sure, maybe Alex will also share some slides or other lecture notes, so she will decide and announce it if there are such plans. But from my side, I can tell that we will do our best to share the recordings, right? So as you can see, this lecture is recorded as well. So if there are no technical issues, then we'll definitely share the recording, of course. All right, I do not see more questions now regarding the organization, so let me now stop sharing my screen. And Alex, if you are ready, the Zoom is yours and you can start sharing your slides. I will soon make you the host.
All right, thank you very much. Hello, everyone. It's very nice to meet you. I will be conducting this workshop for you this week. My name is Alex Linden, and I'm a mathematics student in Poland from Krakow. And my specific interests are dynamical systems, the mathematical foundations of quantum mechanics, and quantum error correction. All right, I will have my own part about the organizational part. The most organizational thing first. Can you see my cursor? That's important to me that you do. Great, thank you very much. Second thing, before I get to the main part, I caught a cold, and so my voice might be slightly giving out during the lecture. I hope that does not happen, but if it does, I apologize. Well, let's talk a bit about the workshop itself. Here's the agenda. You also have the agenda posted on Discord. This workshop is a follow-up on intermediate level to QBronze that I hope you're familiar with, because we will be assuming that you have all the knowledge from QBronze. I will revise things, and of course, if someone doesn't remember something, I will gladly help out. But the general basics are required, or rather recommended. This workshop specifically, I think, is a very nice step to understanding quantum algorithms, because we will be learning some very important building blocks that you will then see if you continue your journey with quantum computing with many other algorithms. And additionally, you will understand them at a deep level, deep enough where if you want to design your own quantum algorithm at some point, I think they might prove to be useful. First day is today, and as you can see, we are doing the largest amount of notebooks. So just to prepare you, today is the biggest risk of going over time. I will try for that not to happen. And today we'll learn just the basics, remind ourselves of things. A very interesting and important, let's say, quantum trick, which is phase kickback. And finally, a full quantum algorithm, which has an advantage over its classical counterpart. Day two will be two more algorithms where you will see, I think you will see the building blocks that I mentioned, and you'll start recognizing them and using them to implement some slightly more complicated algorithms. Day three is the Simon algorithm. One can say the culminating algorithm for this first part of 3 days, which is very important. It's utilized in Shor's algorithm, which is probably the most well-known algorithm, which, by the way, if you would like to learn more about it, then I invite you to join QSilver at some point. Day four, we'll learn a new framework that we'll work with, and that's Circ. And the rest of the workshop will be doing things in Circ. Then we will remind ourselves of Grover's algorithm. And here's the important part where I would suggest that you check Grover's algorithm, because we will not be going through it as thoroughly as QBronze did. So if you want to prepare yourself somehow, then that would be my recommendation. And finally, the day 5 will take a very real and important graph theory problem and try to use it using Grover's algorithm. And this part will also be using those building blocks that we learned all throughout the workshop. Some of you may have noticed, but the day 2 and day 3 were switched because I think it will flow better, since Simon's algorithm is probably the most difficult one out of all of these during this first part. Now, form of the workshop. The lectures are not mandatory. They're, well, conducted through Zoom. You're on Zoom, so you know that. I will be saying, basically, I think the Jupyter notebooks are very self-contained in that you could just go through the notebooks yourself, do the assignments, and have the certificate. So, but I will go through everything step by step to make sure that everyone understands what is going on, and how we derive the things that we'll be learning. Now, in terms of quizzes, I would ask you to remind me at the end of the workshop, after everything. I will show you Canvas and show you in general how it works and what you can do with it. But it was already mentioned, and to receive the certificate, you need at least 50% of the score per homework and at least 70% of the total score for the certificate. Total score is, of course, the sum of all scores that you have gotten. As I've mentioned, we'll be working in Jupyter, so this is another environment I hope you're at least familiar with. And the important thing is questions. So if a question is about something connected to the lecture or an organizational thing, then it would be great for you to ask it on Zoom. But specifically, things that are connected to the lecture and the thing that we are talking about, then the best way for me to hear it is for you to turn on your microphone. But if you don't want to, I will read chat sometimes. And then I can answer also all these questions. All right. Let me see if there are any questions now. Okay, we can go further. Another environment we'll be working in is Discord. And there's a lot of useful things here if you know where to look. Most of the channels are self-explanatory in their name, but the important part I would like you to notice is the help section. If you have any questions about homework or some mathematical aspects or quantum aspects, ones that even, well, are extra questions, not necessarily about the notebooks itself and their contents, then I would advise you to go and search for the channel under help, which suits your question most, because then either me or the mentors will be able to answer it. And one important thing is the rule for the homework channel and the assignments and quizzes, both of them. Because of course you can ask questions about the assignment, very general one. If you're stuck on something, we'll try to help. But please do not post snippets of code in homework. If you have a question of this type, just about your solution to the problem, then please contact some mentors specifically, or me. Okay. Now, in the channel workshops, I already posted this message. And this is a system that was introduced last year, and I think it worked very well, so I will be using it as well. In the Jupyter notebooks, there are tasks. And as this is a workshop, it will not be a complete lecture, but there will be some work that you'll do yourselves. So for example, you see that here is the name of the notebook, the name of the task. I will give, for example, 5 minutes for the completion of the task. And then if you're working on it, after I ask you or just want to specify you're working on it, then please post the moon emoji or click the moon emoji. If you are finished, then please click the full moon emoji. And if you still need more time, then press the clock emoji. It will be helpful because if more people need more time, then we'll give it. If everyone is done with the task earlier, we can also just go forward with the material. Now, I mentioned most of these. These are the platforms that will be used during the workshop. I hope you installed Qiskit at least because we'll be working on it. I advise you to install Circ as well. And there might be some problems with it. I know that there are some collisions and problems, but we're here to help you with those. I said about revising bronze and revising Grover's algorithm. In terms of my notes here, I'll be using OneNote. Most of things that are here will be just parts of the notebooks. I'm using this because I can write on top of it. There will be some extra things I will say and some calculations I will do. And so at the end of each day, I will post both the PDF version and the OneNote version. The latter because the PDF version doesn't always look nice. And I think it might be better for you to just see it as it is here. So this is time for questions now. Are there any questions consisting the organization of the workshop? All right, if not, then we can go forward and start going through the material. First of all, I'll write a couple of things that are preliminaries, or so to say, a revision. First of all, we are working in a vector space. You don't need to know exactly what it is, other than it's a space where we have vectors. And what we're working on are vectors. But there's a special notation that's used in quantum mechanics, and it's called bracket. Bracket because of just brackets. And so we have this kind of vector, which is called a bra, and this kind of vector, which is called the ket. Now, this vector you will see more often, the ket. And the ket is just a vector up to some Vn, let's say. But now we have the bra. How do you construct the bra? The bra will be, so the bra is emission conjugate. And that's also a special notation. And what that means, it's complex conjugate transpose. Essentially, maybe it sounds or it looks more scarier than it is. It will be the same vector, but like this. Now, we can do special kinds of operations. And this is one of the things which I think is very important, but because it might take some time, I will do it at the end of the lecture. We can go to quantum state. Now, we know what bra and ket is. Now, usually we denote state vectors, which is this vector, with psi. This is the most widely used notation. And this you will see a lot, and I think you know it from QBronze. Alpha and beta are amplitudes. And 0 and 1 are base vectors. Now, there are special rules for the amplitudes, which is alpha and beta are in the set of complex numbers, plus the module squared. I'm putting a module here because they can be complex. And beta squared, similarly, is the probability of getting 0 after measurement. After measurement, you can only get 1 or 0 if you're working in a smaller space. Similarly with beta, the probability of getting 1 after measurement. Another important rule is that the module squared of alpha is module squared of beta is equal to 1. That is a very important rule, which actually lets all of this work. All of this being things that we will see today and during the rest of the workshop. Now, another thing we'll use is the superposition. And you've seen the superposition because it can be exactly that. Here, I would like you to think about it not being, them not being, one of them not being 0 and the other not being 1. And what the superposition is a linear combination of base states. Then we can measure the superposition, and this is the collapse of the superposition. And after measurement, you can get 0 or 1. Entanglement I will also leave. So this I will do after the workshop. Entanglement, I will just write the bottom part, and the derivation of it, which is more mathematical, I will do after the workshop. Imagine we have two state vectors. A is a system that we're working in. B is another system. You don't need to concern yourselves with what it is exactly right now. Just this is a tensor product that's important. We'll use it today. So this is basically the outer product. And just in general, if we have just an example so that you can do the tasks. For example, one is 1, 2, 3. Now that's just my notation of writing the multiplication of matrices. And here what we're doing is multiplying each element by each element. And here it will be 2 times 4, etc. Next, circuit representation. What we'll need in circuit representation, I will explain when we get to the Qiskit part. But one important thing, which is a big problem usually, is the Qiskit notation. So if you get a result like this after measurement from some quantum register that you're using, 1, and quantum register of 0, you will think that it will go from 0 and then 1, but it doesn't. The reason for it is that Qiskit is using something the little endian notation, which is supposed to emulate how binary numbers work. So the more important bit is in the front. Now, before going further, I'll see if there are any questions. Okay. So we can start with revising Qiskit. All right, I already mentioned quantum registers. But first we need to actually import Qiskit, which is our library we're working in. And the language we're working in is Python, obviously. But then we need to import also quantum register, classical register, and quantum circuit from Qiskit. Now, with this line of code, we're creating a new quantum register with 4 qubits. Here is the number of qubits, and we're giving it a name. And you can give any name you want to your register. So this is a quantum register with 1 qubit. And when we measure a qubit, it turns into a classical bit. So we create classical registers to store the output or to, let's say, catch what we got from our calculations. Similarly, we can give any name we want to it. We're using the classical register, and this is the number of qubits we're using. Next thing is creating circuits. Quantum computation in the, let's say, most widely used model is a circuit-based. A circuit can be something like this, for example, in a very simplified form. And what it tells us, this is an age. Time flows to the right, so we're going from this side with some state of ours, our qubit, and this is a gate that will apply onto that circuit. And then we can continue our calculations. So we're naming our circuit. We're creating a quantum circuit with the quantum register and the classical register both. You can create the quantum circuit with multiple quantum registers. So here you can put as many as you like, and then the classical register. You can also create the circuit in a different way. If you want to have only a quantum register, you can. For example, if you want to debug something and we'll just be using, we'll be looking at the state during the simulation. Next, also we can create a quantum circuit where we are not saying what registers we are using, and then it will create this quantum circuit, which has 3 qubits and 3 classical bits. This is the standard. You can choose which of these you like and use them. Next, gates. We will be using gates a lot, and the gate-based system is the most widely used system for quantum computing. A gate is what I told you about here. They're represented by matrices. From bronze, you can remember, for example, the NOT gate. You write it as X, and you write which qubit you want to apply it to. So for it, you use the quantum register. Similarly, you can apply the Z gate to qubit 2, and H gate, which is the Hadamard gate, for creating a superposition. A CNOT gate, which you might also know as the classical counterpart, where qubit 2 is the control. So first is the control, and then we have the target. Just to remind you how CNOT works, is if we have a state consisting, let's say, of 2 bits that so this is the control, this is the target, and the control is 0, then the target stays as it is. So for example, 0, 1 will be 0, 1. But if the control target, oh, it's supposed to be 1. So if the 1 is here, then the gate will flip the target and leave the control. So apply the NOT gate to the target. Next, we can create different gates, for example, the control Z. So similarly, just how we're using the gate NOT here, we can also use control Z in the same manner. So again, qubit 0 will be the control here, and qubit 1 will be the target. A swap gate. A swap gate swaps the qubits. Pretty self-explanatory. And here we're doing it between qubit 1 and 3. Very important gate in quantum computing, which we'll hear more about during this workshop and this day even, is the double controlled NOT gate. So I think you might figure out how it works. So those are the controls. This is the target. And both of these need to be 1 for this to have the NOT applied to it. So first we're doing both qubit 0 and 1, and then the target. And you can also apply gates without specifying the register, as you can see here. This is what we've created here. The built-in function draw will show you this diagram. And as you can see the circuits here. Those are the qubits. And this is the classical register. This notation says that there's 4 lines here just squished together. And you'll see the results of measurement here. And as I said, you can apply gates a little bit like you'd apply beats to a necklace. So here we see the NOT gate, the Hadamard gate, the Z gate, the control X gate, C NOT, control Z. You might think, why are those the same? Because we'll learn more about it later, but the order of this does not matter. Swap gate, obviously also the order does not matter. So it's shown like this here, and the double controlled, where you can see the controls here. Additionally, what I recommend, because I think it looks cleaner, especially with larger circuits, is using the draw function with the output specified to be MPL, which is short for matplotlib. All right, we arrive at our first task, where we have to create a quantum circuit with 10 qubits. First, we'll apply the Hadamard gate to qubit 0 and apply 9 CNOT gates where qubit 0 is the control and qubit I is the target for I equal 1 to 9. You might use your Python knowledge here to make your job a bit easier. And next, draw your circuit, either in the regular form or in the form of matplotlib. So now is 1946. So let's see. It's task 1. Oh, 47. Let's give ourselves 5 minutes. So at 52, we'll be back and I will do the task with you. In the workshop, I will also post the task where you can note whether you're done or not. The material is the Jupyter notebooks, which you can see in Discord in important links. You have the QNickel materials. And from there, you need to download the repo and use Jupyter Notebook to be able to use them. All right, it is 52. On Discord, I don't see that many reactions, and it is a good idea to just react to the message because it will let the flow of the workshop be more customized for you and the speed of the group. All right, then I'll share my other screen. We're doing task 1. Is the screen visible?
Yes, it is.
Thank you very much. Okay. So what do we need to do? First, we need to apply the age gate to our qubit 0. But for that, we need to create our registers. So let's create the quantum register. With 10 qubits. And the classical register. also with 10 qubits. This is not necessarily needed for this task. Because we are not measuring anything, as you can see. Now let's create our circuit. We're using the function quantum circuit. Finally, we get to step 1, where we can apply Hadamard gate to our circuit. We're applying to the qubit 0 from the quantum register. Now we need to apply the CNOT gates. So we'll just use a simple for loop. And 1 to 9, when you're using range, the second part isn't included, so it's from 1 to 9. And finally, we need to draw the circuit in the simple version. Here we go. We have our 10 qubits numbered from 0 to 9, our classical register with also 10 bits. First, we apply the Hadamard gate to the 0th qubit. And then qubit 0 is the control for all of these gates, as you can see. And then the CNOTs are applied to each one of the qubits once. We can go back. Then let's talk more about gates then. We can use different functions in Qiskit to have an easier time applying gates. So if you want to apply multiple, like the gate to multiple qubits at once, you will first create a new circuit and then apply it to the quantum register. So that applies it to all of them at once. So the Hadamard gate would be for each one of those qubits. Next, we can do controlled gates. So we have CNOT. We saw the controlled Z gate. We can also have controlled Hadamard, as you can see. So if we want to achieve this, we need to import something. So from the Qiskit circuit library and standard gates, we will import H gate. So in this case, it's triple controlled. So controlled, controlled, controlled H. We're using the function H gate on the controls with 3 qubits. So the first 3 qubits here will act as the control. The last one is the target. We're using it as a list in Python, as you can see. So just like as I told you with the beads on the necklace, we're putting them or appending the necklace, so to say, with the triple controlled H gate. And then we can draw the circuit. We can do all sorts of things with gates. They're very versatile. So you can define other operations. Here we're importing the X gate. So we just want to make a gate which will raise the state to the power of, like, take the root of x, essentially. So for that, we're using the h gate with the power, and here we write the exponent. So next we can also append, well, we're appending the root x to 1 and then join the circuit. All right. Here we have a second task. So again, we'll have 5 minutes for that. So let's say it's 8 now. With epsilon. 2805. And this is the task 2. If you want to ask questions during the break, you can. It's task 2 from the notebook Qiskit introduction. You can, and Umesh, you can submit all assignments before October 18th. Hello there. If you just joined, we're doing the notebook A00 Cascade Introduction. We're doing the second task. And we're finishing doing it. All right, I think we can go further. So task 2. Task 2 is fairly similar. So we have to apply the Hadamard gates to all qubits, then applying the NOT gate to qubit 0, which is controlled by qubits 1 to 9, and then applying the Hadamard gate again and drawing our circuit. First, quantum register, classical register. We can get it from task 1. Then we'll be applying the H gate to the whole quantum register, so to each one of the qubits. Now we can control 9 times, and it's controlled dot controlled X gate, and we're using the X gate function. With 9 controls. Sorry, with control, yes, with 9 controls. Correct. Next, we're using the circuit append. And we'll use range here just to make our lives easier to not have to type it. So first, we'll be using range 1 to 10, as we did. So from 1 to 9, including 9. And here, we need to still add we can use this to concatenate lists, and we'll be adding 0 to that. Next, we can draw our circuits. Although first we still need to do step 3.
Excuse me.
Yes.
Why are you using range twice? I think it should be once.
Oh, that's true. Thank you very much. Me forgetting that I used range already. List range to see parentheses like this. Okay. Should work. We'll see. Thank you very much again. And then we will draw our circuit. Let's see if we have what we're supposed to have. So Hadamard gates on all qubits. Then the NOT gate, 2 qubit 0. So here we have the NOT gate controlled by all of those qubits. And again, the Hadamard gate. Okay, we can go back to OneNote. Next, what if we want to actually get results? We're using a simulator. So we don't have the computational cost of using an actual quantum computer. So if we want to get some statistical information about what we are doing, we can run the circuit multiple times, measure it, and see the results. So a simple circuit here is everything that we've known, creating the quantum classical registers, creating the circuit, applying the H gate to qubit 0, and then measuring both qubits. So we use the function measure on the quantum register and classical register. Next, what we need to do is import R simulator from Qiskit-R. The name is because Qiskit has a few different parts. They're about the 4 elements of earth, water, air, and fire. And the simulator is in the air section of it. So we need to import it from there. The usual way we get the statistical results is by using the R simulator. So we're simulating running our circuit using the run function. We need to provide it our circuit. And then shots is the number of times that we want to run the circuit. Then we get a dictionary. So we get job result, and that's a dictionary. So then you get counts circuit, which will just tell us the elements and how many of different options there are. So in this case, we have 0, 1, 49 times, and 0, 0, 51 times. Let's see if this makes sense. So this is Qiskit order. So because we applied qubit to qubit 0, then this is the second qubit here. So it's either 0 or 1 because it is in a superposition. Now, this is 0 because we didn't do anything with it. Yeah, as we saw, this was measured almost an equal amount of times. And well, here we're talking about the order of the qubits in Qiskit, something that I already told you. So for example, if we apply the NOT gate to the 0th qubit, then the state 0, 0 becomes 0, 1. Again, because the order is, let's say, reverse to the most intuitive way we would use that. We can also measure just some of the qubits. Measuring all of them sometimes isn't needed, or very often isn't needed. So here we want to measure the qubit 0 first. So we're getting 2 qubits, one on classical register because we just want to measure 1 qubit, creating a circuit, applying the Hadamard gate to qubit 0, measuring here, and we're using the quantum register, qubit 0, classical register, bit 0 from the classical register. Now what we already seen, we're using the simulator, and on it we're using the function run. On our circuit, we want to run it 1,000 times. We get the results by getting the job result and then counting it and printing it. So here we got 1, 516 times, and 0, 484 times. If we apply a Hadamard gate to a qubit that's in state 0, we have a very nice superposition because then we can get zeros and ones with equal probability. Next, we have another task, which I think it's useful to do. So here it will also be 5 minutes, but if you need more time, then please click the clock. So let's see. It will be from 8:15 to 8:20. See you then.
Sorry, what's the number of the task in the notebook?
Number 3. I'm changing it right now here. Hello, thank you for the question. We chose it arbitrarily, but if you run the circuit more times, then you will get a better result that is closer to the actual state. So for example, if you run the circuit just twice with the Hadamard gate, you might get 1-2 times. You cannot really draw anything from that. But if you run it 1,000 times, the number will get closer and closer to 50%, which is what it is in reality. Yes, you will have access to the recordings. We do the tasks in Jupyter Notebook from the repo that's provided in important links channel on Discord. Oh, thank you very much for letting me know. I'm putting it in there just in case if a lot of people need more time. But we can go to completing it. So we're implementing the circuit in task 1. I copied this part from task 1, which we already discussed. But now the task proper is to simulate it. So first we'll measure the circuit. With the Q quantum register and the classical register. Next, we'll do job equals. Of course, you can put a different name here. This is just how it's used in these notebooks. And later. We're running the circuit here. And we want to run it 1,000 times. Finally, to get the results, we're getting the counts. So from job, we're getting the result of the simulation and then counting it. With their circuit, and finally we're printing counts. Let's see. We have 10 qubits, so it's good that we have 10 bits here. And we are getting a result which we would expect. So we're just getting ones or just getting zeros. What did we have in task 1? Let's see again. So first we're using the Hadamard gate. And then if it's 1, we're changing all of these to 1. If it's 0, we're not doing anything with it, so it will be all zeros. So that is about what you will expect. Now, if you want to cheat a little bit, because we're using a simulator, not a real quantum computer, as you might remember, if we measure our state, it will collapse to either 0 or 1. So during computing everything and putting the gates, we don't know what the state is. Usually we can know because we know the gates that we've applied and the states we have set our circuit in, but it is kind of a black box. So, but here you can look into it and see exactly what is going on and what kind of vector, state vector we have. So after applying the Hadamard gate here to the qubit 0, we're using the state vector simulator. And this you need to import from Cascade Air as well. And we're running the circuit. So then we're doing state getting the result again, and then using the function getStateVector with the decimals for it to be as precise as you'd like. And then we're printing it. So what do we have here? We're expecting to have an equal superposition of state 0 and 1 on qubit 0. Now, why do we have the 707 or 0707? Now, if we apply a Hadamard gate to state 0, what we get will be this state, also known as the plus state. And why these amplitudes? Because this is an equal position, superposition of states. You can also calculate with the matrix of Hadamard, which will be yes. So if we raise it to power, if we square it, then we have 1.5 and a half, what we want. But here we just have 1 divided by the square root of 2. And on the other qubits, we didn't do anything. So it's 0 as expected. And the dimensions here. So the dimensions kind of tell you how to view this vector. In this case, the first two will be above, the other two will be below. I wouldn't say it matters that much. Well, yes, if you measure a state in a superposition, if you measure it, you collapse it, or you collapse the wave function, where you will just get 0 or 1. So here we're measuring the quantum register, the classical register, using the state vector simulator again, and running the circuit. And we're getting the state with, again, the signals and printing the state. So now we can only get 0s or 1s. Here, we got a 1 in our 50-50, and all the rest are 0s. And again, the dimensions remain the same. Here, the task 4, I think we'll skip this one. Of course, you can do the task yourself, and the proposed solutions are also inside the Jupyter notebooks. Lastly, for this notebook, we have the unitary matrix representation, where if we have a gate, we can represent it as a matrix. And this gate is acting on our state, which is a vector. So what we're doing here is we want to get the unitary representation of the CNOT gate. So first we're getting the here root x gate, what we already did. So square root of x. Then we want to see the matrix representation of the CNOT gate, and then of the square root of x gate. If we run it, we get something a bit strange, because let's see what we have here. We have ones here, 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 and here. But this doesn't seem to make that much sense. because with the CNOT, we're expecting the ones in different places. But here we have to note the cascade order. Something that I've already discussed. Oh. So what we're expecting here would be the CNOT gate represented, let's say, normally. If the first bit is 0, nothing changes. So we get the identity gate here. 1, 0, 0, 1. That's the identity gate. But if the first number is 1, then the second one flips. And it flipping is a NOT gate, which you probably also know. And here we're just filling it with zeros. I think that makes sense. But we're not seeing this here. What is useful in situations like this is to write the input and the output of what you expect. So for the inputs, 0, 0, 0, 1, 1, 0, 1, 1, we're expecting the outputs 0, 0, 1, 1, 1, 0, 0, 1. If you read it from the other side in the cascade order, it should make sense. And in this case, if you remember, the easy way of reading what is going on actually is assigning all the inputs here in the lexicographical order. And here's what we get. So then you can see from the input or to the output if this is what we got. All right, so for example, as you can see, 0, 0 maps to 0, 0. And similarly, the other one should work as well. I hope that clears up some things because I know there can be the confusion here. I hope that is clear. If not, then please ask a question. Next, the matrix representation of the root of X gate. Here is something we would expect. Note, please, the pluses and the minuses. I will not stop here for very long because this is not as important as the CNOT gate representation was, in my opinion. Next, we're using another example. So quantum register with 2 qubits, a circuit. We're applying the Hadamard gate to all qubits, and then we can use the unitary simulator again to get all the possible states. And here you can see everything being in an equal superposition. So this is again what we're expecting to see, since we're applying it to each qubit. So if you look here, this portion, it's essentially the Hadamard gate. Here the amplitudes will be different, but you get similar results. All right, so now we finished this portion. I will be answering questions now if there are to the entire notebook. But since we're going from notebook to notebook, and we don't have much time today, so I think it will be only a 10-minute break. So let's say 35. 245. All right. So far, maybe nothing interesting in the quantum way, but we're getting there now, or in 10 minutes rather.
So may I have a question?
Of course.
Yes, I would like to ask about unitary matrix representation that you showed
Yes,
recently.
yes.
And if you could go to the slide. Yes, I understand what's happening on the right, yes. And I'm asking myself, what, because if we look at this list within list, yes, list within list, we can see that the first row can be like the first column, yes.
Yes.
It could be the same as in the CX matrix that you
Yes.
drew,
Here is
yes,
also one.
that you drew. And then when we take the second verse, yes, the second row, we get the one at the bottom.
Well, second row, here we get one here, but if we take the second column, we get one here, yes.
Could you explain why?
Yes. So normally the CNOT gate would be like this. If we have, this would be just a mapping from the input to the output. 0, 0, 0, 1, 1, 0, 1, 1. We'll
Yeah.
map it, here it's 0, so it's not changing. 0, not changing. 1, changing.
Yeah.
1, changing. But what we need to do here is look at it in the reverse order. So if we look 0, 0, 0, 0, it's the same because it's symmetrical. Now, if we look at the second thing and read it in the other direction, we get 1, 0 mapped to 1, 0. And we have here 1, 0 mapped to 1, 0. Similarly here, if we look at it in the cascade order, so from, well, the second bit, let's say, in our normal way of looking at things, it will be 0, 1 to 1, 1. 0, 1 goes to 1, 1.
Yeah.
Yeah, so this is why it works like this. And then in the way I propose that if you read it, so 0, 0 goes to 0, 0, then here you'd have 0, 1. What does 0, 1 go to? 1, 1, because there's a 1 here. And similarly go about the other ones.
Okay, thank you.
Okay, if you have any other questions, then please don't hesitate to ask.
So maybe one more. As a matter of fact, when you, as you now have written 0, 1 over this column, yes. So at to the right, it would be 0, 0 from the side, yes.
It's 0, 0, 0, 1, 1, 0, 1, 1. And similarly here, 0, 0, 0, 1,
Okay, the
0, 1,
same.
1. And you read it in this direction. So the thing from the top, so 0, 0, becomes 0, 0. And 0, 1 in this direction becomes 1, 1.
Okay, thank you.
You're very welcome.
Hello?
Hello, yes.
Hello? I have a question. My question is the first bit is the control gate, the control bit, and the other is the target, or the vice versa.
The first one, or rather, okay, the first one is the control, but we can have a lot of controls. So this, this could be just one control, or it could be 3 or whatever. And then we have the target.
We just have one target. We couldn't have many targets at the same time.
Well, no, because if we have a controlled gate, maybe we can see it somewhere here. It's like, for example, the controlled Hadamard. This means that if we have the 4 places here, and those are our controls, and this is the target, all of these have to be 1 for this to flip. If any of these is not 1 but is 0, this will not flip.
Okay.
Because we're using 1 qubit gates here. We have only 1 target. Did I answer your question?
Okay, thank you.
Great, thank you.
Yes, thank you. Yes.
Welcome back, everyone. We will be moving forwards to the first notebook, where we'll do some interesting computations with quantum registers. Let's go to the beginning. We'll be talking about classical gates. And first, the computer scientists among us probably know what those gates are, but they are very intuitive. Most of them are. So for example, we have a 1-bit gate, that's the gate NOT. So it negates the input. So for 0, we get 1, for 1, we get 0. Then we have the NOT gate, which works only if 2 statements are true. And here I will point you to one thing that is, let's say, a caveat in the theory of logic. Here, if I say, I will go to the park and I will go to the cinema, that means that both of these are true. So only if I go to the park and then the cinema was my statement correct. For all the other ones, it's incorrect. This is the same as in natural language. Next, we have the OR gate, and this is where I would like to note the difference. So the OR gate, what I would say in natural language is, I will go to the park or I will go to the cinema. And what I mean to it, that I will either go to the park or the cinema. If I go to both, it's not really natural for us to say it that way. But the OR gate works in a way where if both statements are true, then it still will have 1. Now what we're looking for is a gate that will be very useful later on, is the XOR gate, or exclusive OR gate. So it's exclusive OR because only we have to have exactly 1, 1 and 1, 0. So only these two will give us 1s, and 0, 0 and 1, 1 will give us 0s. All right, we have the first definition of a universal set of gates. There will be a second one, so I will just mark it as 1. So a set of gates is universal if it can implement any Boolean function f going from some string of 0s and 1 to 0s and 1. And what this means, of the function f going from 0, 1 and to 0, 1, let us choose our n first. So n can be 3. And then to each possible base state, so here it will be 0, 0, 0, 0, 0, 1, 0, 1, 0, and just like that until we reach 1, 1, 1. To each of this, we need to decide what the value will be. So this can be whatever function. And the output will be just 1 bit, 0 or 1, 0 and 1, 0 and 1, etc. And of course, we need to use the gate set to achieve this. For example, a universal set is the AND or AND NOT gates. So yes, I said all this so we can proceed further. Okay, we have task first, and there are some tasks where we need to discuss things. And I think it would be really good if there were some ideas. I think this task specifically is quite difficult. But I would like to know any ideas of where to go from there. We want to implement AND, but we don't really have AND as as a quantum circuit. You can think about, for example, why is that? We'll learn it in a second. Do we have the NOT gate? Yes, we do. It's X in quantum, let's see, quantum world, we have X gate. But we don't have AND, we don't have OR. So first, we'll answer the question, why is that? And yes, if you have any ideas, you can either say it through your microphone or write it in the chat. And here there are no wrong ideas, really, because the task is for, I would say, your reasoning more than actually what you know, because we'll learn it in a second. And then how we can implement it. So the second part of the question is, what gates do you know? And are any of the gates similar, the quantum gates, to AND and OR? So without providing time, I will just give it 2 minutes. If there are no answers by then, we will proceed. So until 8:53. All right, we have an answer. It assumes it has value to consider. And given the superposition state, there's no certainty for input until the qubit is measured. Yes, I would say this is a very valid answer. However, we can, if we just say, I'm working on state 0 and 1, because those are the outcomes of measurements, and outcomes of measurements can be zeros and ones. What you said here, I would say, is part of the answer and partly not the answer, but I think it's very good reasoning. So thank you. Okay, I think we can proceed. So here we have the answer to the first part that I asked, why is it not possible? There's something called reversible computing. So let's do a test, just based on our understanding on reversible. It means that if we cover up the input and we just see the output, we can say what the input was. So, of course, knowing how the gate works, we know that gate not is negation. So if we say, I got output 1, that means that the input was 0. And otherwise, if we got output 0, we know that it's 1 with certainty. Now, the same cannot really be said about AND and OR. Let's take AND as an example. Does anyone have idea why is that? Why is this not reversible? Again, you can
Because
look
it's
at
not
it.
a function as you defined before, you know.
Well, not necessarily, because we defined it as here n is 2. So we have input 0, 0, 0, 1, 1, 0, 1, 1. There can be no other outputs. And to each of those, we're assigning the value either 0 or 1. And this fulfills this condition. So yes, Mark, this is the answer. If we look For example, at 0, 1, and 1, 0, and 0, 0. For example, if someone tells you, I got 1, because we know how AND works, we know that both the statements were correct. So here, there's no problem. But if someone tells us, I got a 0, well, it can be any of these 3 options. So in this way, it's not reversible. And here, I think there's a mix-up of 2 different ways of looking at this. And I will try to clear things up maybe. Because, again, I know we have a lot of people from STEM here, so I sometimes might tell something more to the mathematicians or the computer scientists or the physicists. So in this case, the physicists and the computer scientists might have a different notion of what reversibility is. So first of all, we cannot guess what the input is. That's what we discussed right now. And then we can say that the information or the entropy is lost by applying those gates. Now, entropy can be seen as a measure of information, of the amount of information. In many different fields, it's defined differently, so I cannot, or rather I would not choose just one formulation right now. So entropy is lost, and that's why they're reversible. Those are a bit of 2 different things. We'll see in a moment. Irreversible computation, well, I see this as a typo, dissipates heat to the environment. And this again is about the entropy. But I will specify what it means in a moment. So as I said, the NOT gate is reversible. Just by looking at the output, we know the input. And gates that are in the set of reversible gates, so it will be reversible computation then. Here, you remember we had the definition of a universal set of gates? We have another one here. So this is the second definition. So a set of gates is universal if we can implement any other gate using the gates in that set. So what it means, for example, we have a set of gates and NOT. By being clever with the operations, logical operations like negation or using AND or, this is allowed, and we can construct any other gate with this set. So yes, it is possible to build a universal computer which only uses reversible gates, theoretically. We'll try to see how that works. So for example, AND and NOT gates are a universal set of gates. And the important thing, which we'll discuss in a second, is the defaulting gate, which we have already seen today, which is the double controlled NOT. And they are used for classical computing. But this gate is important because it's also a quantum gate. We implemented it on a quantum circuit. So this is an interesting conclusion. Well, this might be a little bit of a tangent, but we live in a quantum world. And what it means, well, we can say that the classical world is a bit of a subset of the quantum world. Because if we go to a very microscopic level or macroscopic level, the things that we know just with classical tools start not making sense. And that's when quantum comes in. But all the things that are classical can be explained by the things using by the tools provided by quantum mechanics. So for example, since we have this gate, it's a universal set of gates of one gate. And it's both classical and quantum. That means that we can simulate any classical operation using a quantum computer. Yes, exactly. You can also use NAND and NOR gates. Also, especially the one with NAND, is very useful. There's multiple sets of gates like this. Now, if we want to have gates and OR, just like we discussed in the previous task, then we need to implement it in a reversible way. And here is something that you'll see a lot of during this workshop, which is if we create a 3-qubit circuit where these are the inputs. Oh, okay. Well, x1 and x2 are the inputs, and they stay the same at the end. And y is the, we can say the target qubit, and we implement this operation. Now, we'll explain it in more detail later, but this operation is the exclusive OR operation. No, wait. Yes, it is. So it's bitwise addition modulo 2. I'll explain it later. Now, just to quickly say what I was talking about with the first part of this, is we have two different notions of reversibility. One is the physical one, which the physicists may know better, and the second is the logical one, which the computer scientists might have seen. So a process is physically reversible if it is isentropic. And if it is isentropic, what it means, it does not lead in an increase in physical entropy, which already we see here. So the entropy is lost. Now, what is entropy? I have my favorite example of explaining entropy is if we have a glass and we have some tea and some milk, and we perform an operation with a tool that's a spoon of mixing it, what will happen is the milk and the tea will mix. So let's see, we can see what happened here. We mixed it. We can even record it. But if you get the output, this should sound similar, then we cannot know exactly, where the milk was. We cannot reverse it. And this is what entropy is. It can also be seen a state of disorder in this case, right? So this would be an increase in entropy because the disorder of the molecules inside increased. And what the isentropic means in a different way, I'm wondering whether to write this. I will write this. This is not, that's very extra information. This is adiabatic plus reversible. We have a notion of reversibility now. Adiabatic just means that it's a process that occurs without transferring heat or mass to the environment. So this is, I brought it up because here we say that irreversible computation dissipates heat to the environment. That's what was meant here. And in all the other places, we mean that the process is logically reversible And that means that the operation, then the output can be computed from the input and vice versa. This we discussed. Are there any questions to this part? Okay, let's proceed then. We have another task. And since, again, we don't really have much time, we only have an hour for a lot, I think we might be over time a little bit, but in that case, the recordings will be provided. So we have a table that is corresponding to a reversible AND gate, where again, x1, x2 are the inputs. And so this is the input of the AND gate. And then we have y. So in this here, we have the y, but we set it to 0. So first we want to see, let's do it together, what we'll get. So 0 and 0, here we have the XOR. So x1 and x2, 0 and 0 is 0. And we're XORing it with 0, getting 0. So here we have 0, 1. Again, the AND doesn't apply here, so we have 0, y is 0, we get 0. Similar things happens here. But if we have 1 and 1, this is 1, this is 0. So 0 XOR 1 is equal to 1. So we'll get 1, 1, 1. Okay, does this remind you of any quantum gate that we have based on the inputs and the outputs? Again, hard question, I'd say. Okay. Do you remember the double controlled CNOT gate? Right? So we remember that both x1 and x2 need to be 1 for the second bit to switch. And we only have one instance where they are both 1s. And y is 0. So since y is 0, it will get flipped to 1. So here's the implementation. Now, I think I will go back to it. So here, either I will do it after the workshop with extra time, or I will fill it up and just send it to you as lecture notes. This is extra, not included. But let's take a look at the Toffoli gate right here. So here we have the table representation of the inputs and the outputs. And the only change between those, it's basically an identity gate up to here, where they switch. Why? Because we're putting the X gate on the last qubit. This is how the circuit will look. Right here, it can be X1, X2, and Y. So in that case, I have an extra task, which, well, I think it would be a good practice to try it. Also, just to familiarize yourself with the way we're working with logic here. This is not, again, it's extra. You can post the answers on Discord, for example, what you got. But essentially, it would be good to implement the NAND gate and the FANAD gate. This is a universal set of gates together, so it's also very useful. What's the NAND gate? So it's the Basically, well, let's start with the fan-out gate. The name is suggestive. And what it means is if we want to, let's say, spread one of the states. So if we have A here, we would like A and A to be spread just to two different points. It's very useful. So with the NAND gate, let's maybe draw the table. So 0, 0 gets us 1, 0, 1 gets us 1, 1, 0 is 1, 1, 1 is 0, just a negation of end. And this is what, again, if you'd like to practice, you can do it in your own time and post the answer in Discord. Next, we want to design a reversible circuit for implementing the OR gate and testing your circuit on all possible 2-bit inputs and measuring only the output bit. All right, let's have 5 minutes for this task. I think the useful part is just the thinking that you have to do to try to come up with it. If you don't, that's all right. It's not very intuitive at first. So, task completion. It will be 5 minutes again. Task string again. So it's 9, 12, 9, 17. If you're struggling with this task, there's multiple different ways of approaching this, but the one that I will be showing will be only consist of controlled NOT gates and double controlled NOT gates. All right, I just wanted to give you exactly 5 minutes for it because I think if you don't have an idea, it will be hard for you to do it. But the thinking, if you did something here, I think it's very good. Well, let me switch. Okay, and we can write some code. So I said my approach, or the approach that is presented here, will be using just CNOTs and the Toffoli gate. So first of all, we want to set our inputs. We'll do it in a very classical programming way. So if we have an input 1, that's only we're doing the initialization. Why is it 0 here and 1 here? Again, because of this cascade order being the opposite. Here I see a problem with indentation. Should be solved now. And if our input 1 is equal to 1, similarly, we apply the X gate 0 this time. So now what are we doing? I will first write the code, then we'll see what happens, and then I will explain. So first I will apply here it should be 1. So my circuit 1 dot 6 zero control to the target. Next, similarly, 1 the control into the target. And finally, the Toffoli gate. So double controlled NOT with 0 and 1 as the controls, and finally 2 as the target. Mm, let me see. Oh, I see. No, I don't. If anyone sees the
You need to make
mistake,
a measurement.
that's true. I forgot it. Thank you very much. And 1. All right. So what I would like to do here, so maybe before measuring it, let's load the circuit so that we see what is going on. Mhm. So the other output. I'm not seeing it, but that's okay. I can draw it for you as well in a second. But let's see what the results are. So only for 0, 0 do we have 0. And for all the other 0, 1, 1, 0, 1, 1, we have the first is, we have ones. Is this the result of the OR gate? Yes, it is. But now I would like to switch. Oh yeah, my circuit 1. Sure. Oh, okay. Let's see. Yeah, sure. Thank you very much. Okay. So first we're setting up the qubits. So yeah, if the input is 1, we'll be switching them. So here, if our input for the first qubit in our order, but it's is equal to 1, we are applying the X gate. And here we're also applying the X gate. So we are applying the X gate to 2 qubits. This is what this is. Then we're applying the controlled NOT, to 0 being the control, 2 being the target. Next, we're doing the similar thing. So what does that mean? If those two have to be ones, right? So if this is 1, then this will switch from 0 to 1. But again, if this is 1, it will switch. So imagine if we have the state 1, 1. So here's 1, here's 1, so it will switch from 0 to 1. Then Q1 is also 1, so we're switching again. So we're doing, now it's 0 again. And that's not what we want. And these two would work for all the other 3 options. But here it doesn't. So we're including the Toffoli gate just to make sure that this last case works for us. So in the case that we do the doubles flip for 1, 1, we'll flip it again, resulting in 1. If you want to check it more in depth, then you can just draw it on paper. All right. This task we will skip because it's quite time consuming. Now, implementing the Boolean function. So we have seen a set of universal gates, and it is possible to implement any Boolean function. That's good. That is what we'll need for next algorithms. So if we're given any Boolean function like that, f of x, we will propose a circuit to implement it on a quantum computer. This is a bit similar to what we saw here, except here we cared about x1 and x2 staying the same. And here we just have one input x and the second y, and we're using XOR for it with our function. Now, we have a black box UF here, but the operator that we're doing is basically it will take xy. So from x to state x, we're not doing anything. From y to the state here. That's all we're saying right now. And this, as we know, is XOR. So again, the mapping is reversible. I think there are exercises to check it later. But F might not be invertible. So that's the advantage of quantum computing, actually. Here I already told you about this, so I can move this blank. And we have task 5, which we want to prove that UF is reversible by showing that given x and y x or f of x, y can be computed. I just want to say that if the task in this notebook proved to be hard for you, I would say they are. And then other notebooks have a bit easier tasks. So here we have 2 hints. So x or x is equal to 0 for any bit x. And this operation is associative. What does that mean? Well, that means if we have A XOR B XOR C, and we put parentheses here, this is the same as doing this, as associativity. And again, I will give us 5 minutes for that. And here, if you don't know where to go, then I would say it's useful, first of all, we want to prove that it's reversible. So what we want to show on the left side, so if we take this result and cross it again with our function, something will happen here, which is the proof, and then we'll get y. I think I will show the timing for it here so that you have the notes that I made. So we have from 9:30 to 9:35. Please mark if you're done with the task. If there's enough people that are done, then I can speed it up. Yes, Richard. That's a good answer. Okay, we have some people ready, so I think we can proceed. So this actually proves, well, maybe difficult to think of, but easy in terms of what it is, because this will be equal to this whole thing. We're using associativity first. So we're writing this and just moving the parentheses like so. Now, where if we XOR something with the same something, we get 0. So this means we have 0 here, because f of x is the same as f of x. Well, now what we get is y XOR 0, which is y. So congratulations to everyone that got it. Now, task 6. I think we'll just do it together. It will be faster that way. So what do we have? We want to apply the operator UF. And what is the state of the output qubit y in terms of f of x initially? That might sound a bit tough, but what we have is two situations where we have x here and 0. Oh, well, we have x here, something here. Yeah, we have 0 here, so that's the first case. That's our y. But here what I forgot is the UF will be applying. What we get is x, and let's calculate it. This will be 0 f of x and then just f of x. And similarly, the second part, if we have x here and 1 here, here we still have x, we're preserving it, and y XOR f of x in this case will be equal to the negation of f of x. Why? Because if f of x is 0, then we have 1, 0, and that's, so if we have 0, then 1 with 0 is 1. If we have 1, then y is still 1, and f of x is 1, but we're doing XOR in it, so it's 0. So that's why it's negation. And for this one, we'll see in the other notebook. So now we'll take a break, 10 minutes. I think what will happen is we should be able to go through face kickback in half an hour and Deutsch in half an hour. So I think the workshop proper will be the 2 hours, but because of the organizational things, it will be a bit longer. Yes, Mateusz, I could have. I also could have just not written anything. It would default to text as well. But I think the Matplotlib one is better. right, the break is over, we can continue to phase kickback. So the one thing to remember is the use of the UF here and putting the XOR here to just have our input and then be able to compute it and the output in a reversible way. Now we're going to phase kickback, which is a very interesting quantum phenomenon at heart of many algorithms, quantum algorithms. But first, we need to tell each other what is phase to not have some wrong ideas, because there are two types of phase. So let's say we have, well, this would be in a specific notation, I theta, where and our state vector. So this, why is it like that? Because the representation of the complex number z can be written as r e I theta. But don't worry about it too much. I'm just writing it because like it's more of the formal definition, but still can be understandable, I think. So we can say that this is equal to just psi up to the global phase factor. So here we have what global phase is. Why is it equal to that? Well, it has to do with quantum mechanics and is quite difficult in itself because of the theory of quantum measurement. However, what you can remember is that if we're dealing with global phase, so something is in front of our state, like entirely in front of our state psi, then statistically, it will be the same. Now just here to be, this is a real number. Okay. So this will be the same. Today we'll be dealing with putting a minus in front of the psi and seeing what happens. But also we have relative phase. So I will say statistics just what I said. But so that we have it in the notes. And then the relative phase. We can see, for example, two states. Valid state and another valid state, which you may recognize when dealing with the NOT gates and the Hadamard gates. You might get this state. So the amplitude of 1 here will be one divided by the square root of 2. And here the amplitude of 1 is equal minus 1 divided by the square root of 2. So here the magnitude of the amplitudes is the same, but they differ in sign. And this is what relative phase is. You can imagine it as being inside of the state in a way. So global phase, you can see the phase is outside entirely. Here we have a phase that is inside. So this is statistically different. So A and B will differ by relative phase, just to have a similar sentence. So if there is a real theta such that A is equal E I theta B. So here we again have this representation. Yeah, and those are two states A and B. Okay. So this is all we have to know to not be confused, I'd say. Eigenvectors and eigenvalues. So here, well, this is very important. And I imagine if you work in STEM or do things in STEM, then during your university years, you probably worked out one of the examples where you need to calculate eigenvectors and eigenvalues. If anyone asks me to provide a written example of the whole calculation of some example, I will provide it. But for our purposes, to see what eigenvalues and eigenvectors are, well, so what is A? It's an n by n matrix. So it's a square matrix. Dimension is n. So V here is an eigenvector or eigenvectors of length n. And lambda is called the eigenvalue. This is a very important concept in mathematics, and we will come back to it a lot. Now, just to have the basics of calculating it, the eigenvalues and eigenvectors, the important part is just to know that for this equation to have non-zero solutions, we need the determinant of A minus lambda I to be equal 0. And if we calculate this, we'll get something that's called the characteristic equation or characteristic polynomial, and we'll get our values from there. So that's what it is for now. Yes, we'll be looking at phase kickback, as you can see from the title. Now, this is what I already showed you. V doesn't have to be with the arrow that I drew it with. So we'll talk about eigenvalues of a quantum operator in other notebooks. But for now, we're thinking of a state minus. The state minus is what you get when you apply the Hadamard gate to state 1. And then let's check the effect of applying not operator in the quantum state minus. Okay, if we have not, well, this is the minus state. So what will happen is we'll flip the minus, we'll put a minus here. The minus here will change into a plus. So we'll essentially get minus, minus, where the bigger minus is the minus state. So we can see that not minus is equal minus, minus, which is similar to this equation, if you can see. So not, remember that gates can be represented as matrices. And we have minus, which is this state. And then this here will be the eigenvalue. So now, task 1 what is the other eigenstate of the not operator? And what is the corresponding eigenvalue? Let's calculate it together now. So, well, let's calculate it like this. Since we said what the matrix is, let's use the equation I provided here. So, well, here, not lambda I equals 0. So this will be determinant of minus lambda 1, 1. If you spot any mistakes during my calculations, please let me know. And determinant will multiply this by this and subtract the multiplication of 1 by 1, which will be lambda squared minus 1. And this is lambda minus 1, lambda plus 1. So first eigenvalue is minus, second eigenvalue is minus 1. And okay, what is the corresponding, what will be the corresponding eigenvector? Here, not to write it the very formal way. If you have not plus, notice that it will be not that's what the plus represents. And this will be essentially 1 divided by the square root of 1, because we're using not, plus y divided by the square root of 2, 0, and that's equal to the plus. So the eigenvalue is 1 for the eigenvector, which is the plus state. Now we'll observe the interesting effect first. So let's say that we have a first qubit is in state 0, the second qubit is in state 1, and we're applying a CNOT. Since the first qubit is in state 0, the CNOT will not have any effect and it will remain the minus state. However, if it is in state 1, then it will have minus 1 minus, and we're seeing this from what we calculated here. Why? It's a CNOT, and we know how NOT works on the state minus. So now let's say the first qubit is in state of the normal one, the alpha 0 plus beta 1. And the second qubit is in state minus. So we have such a state. Those are the amplitudes alpha and beta. So if we apply CNOT, let's see what happens. Well, here is 0, so it will have no effect. But the second one, here we have 1, so it will again act like what we described here. So in the end, if we put the state minus in front of the parentheses, we'll have alpha 0 minus beta 1. So the state of the qubit after the CNOT will be changed like this. And this is called phase kickback because the amplitude of 1 of the first qubit changes sign. So you can see how, well, if we have minus here, this is global phase. It does not matter. Well, statistically, it doesn't matter. Mathematically, it might. But then what we have here is relative phase. So this does matter. So here we see it is a very quantum trick in nature. So in other words, the eigenvalue is kicked back to the control register. And that's just the circuit of what happens. And we want to implement the circuit. I think it will be useful to do so. So we have task 2, 5 minutes for it. Let's go back to it. No, I did not post whether people are completing it on time. So I will do that still. Just in case a lot of people need more time. But for now, I think we'll continue. All right. So what do we have to do? Well, we're creating a quantum circuit with a QReg register of 2 qubits, setting the state of first qubit to 1, the second to 0, applying the Hadamard to both qubits, applying the CNOT. That's essentially what we did here, and then applying the Hadamard and measuring the outcomes. First, just doing it in the way that we have been doing so far. My circuit here is also with the one in the name. Quantum register and classical register in the circuit. So far, nothing new. All right. And then guess I'll just copy that. And we're putting an H gate onto the quantum register and qubit 0. Well, first we need to apply the NOT gate. We need to change the state of the first qubit to 1. Oh yeah, true. I am forgetting the ones. Everything is with ones here. Then we're putting the circuit, and now we're doing the Hadamard gate. For both qubits, the entire register. And then we're putting the CNOT. Quantum register 1 and quantum register 0. Next, we're doing the same thing that we did here, applying Hadamard. Measuring the outcome. Hmm. And then here 1, 0. Wait, no, I'm not doing it correctly. We need to just put the quantum registers here. Oh, again, forgot the one here. In 15. Here we go. And another one. Oh, I see, I see. Okay. We start in the quantum state 0, 1. And state 1, 1 is observed 100 times. Now we'll analyze why that is. For that, we'll switch back to OneNote. All right, let's do some maths. So we start in the state 0, 1. So before the CNOT, we have state 0 on the first qubit. Apply Hadamard, get the state plus. Next, the second qubit starts with 1, and so we get the state. So we get the state plus here. We get the state minus here. Now, we're putting it in terms of the composite systems of the first qubit and the second qubit. So now, CNOT will affect the target qubit when the control is equal to 1. So now we can rewrite it in a way to better suit our needs, which is, so now we'll get the zeros. We'll have 1 divided by the square root of 0. And here we will just have the state 0 and 0. Next, if you look at here, we'll get the state so well here it's because we have 4 different possibilities: 0, 0, which is the first one, 0, 1, 1, 0, and 1, 1 that we can see here. That's why we are rewriting it in this way. You can see it as like propagating it to those 2 places, and this we're splitting. Arithmetically, it works out. So it flips the state of the second qubit. Why? Because this is 1. So when the control qubit is 1. Okay, next, after CNOT, we have this state, which is 0. It remains unchanged. And in this case, we're using NOT. So we're switching. Those are swapped. So the last equation, we can write it as, again, let's take 1 divided by the square root of 0. And then we get, in the second qubit, either 1 divided by the square root of 0. Oh, well, this is all the same, obviously. And here, we're seeing phase kickback. So here, we need to change signs. And then we can reorder it in the way that we want. So the 2 states are separable. And here we have the minus state and the minus state. So here the sign is flipped. Now if we applied Hadamard to each qubit, again, well, this will be 1 and this will be 1, because that's what we get. Hadamard gate will be reversible, obviously. Next task is task 3, and this will skip. And lastly, for this notebook, we'll do phase kickback in general. So what we've learned previously that we can implement any Boolean function in this way. And that's the result of it. Now, let's see what happens. This was the task in the previous notebook, where if y is the minus sign, and let's see what uf does. So if we have the operator uf acting on the state x, which is the first qubit, and minus, which is the y here, we're doing uf on x, and here we have the minus state. Let's bring the 1 divided by the square root of 2 to the front and multiply the uf and x by what we have in parentheses. Again, that's just arithmetic. Next, it will be 1 divided by the square root of 2. And see what uf does. Well, it will change our state to x. It does nothing here. But 0, it will change as f of x or 0. Similarly, this will be the same, but with 1. Now, let's bring the x back again. So now we can see that what we have here is the state f of x minus f of x XOR 1. Here is a clever way of writing it, where we do, because we just have to check whether we'll have the minus in front or not. And this I would suggest that you work on paper, to go backwards. So if you could go here and just see what the value will be if f of x is equal to 0 and f of x is equal to 1, just so that you get a better understanding that we can write it like this. And we brought most of the things out of the parentheses. What is left will be 0 and 1. And here we can reduce it to the minus 1, x, and here we have the minus. This is the hardest part. I don't know, if someone asked me to write it out, then I can, but I think the best way of understanding it is to just see how it works on paper by yourself. So this is how our transformation works. So now, depending of what x is, we'll have different values of f of x. F of x can be 0 or 1. So here, we'll either get minus 1 if f of x is 1. We'll get minus 1, or 1 if f of x is 0. So again, we can see when f of x is 1, the phase is kicked back. So this is, again, phase kickback, and this is the general way of writing it, more generalized than what we did before with the example. And this is what we see in many quantum algorithms. All right, let's take a 10-minute break and continue. All right, hello. Sorry for the delay. Well, now let's look at the last notebook. I think this is a nice culmination of today, since we'll see a quantum algorithm where we can apply what we learned and see an advantage of a quantum algorithm. So first, we have Deutsch's problem, which is first we have a function from 0, 1, so it's just 0 or 1, to 0 or 1. So we have two possibilities. Well, we have two possibilities here. If it's in output here, can be 0, 1 or 0. And now it's balanced if f of 0 is not equal to f of 1 and constant if they're the same. So an example of this for example, 0, 1. This is our f of x. And an example of this would be if they're both 0. So now we have something that's called an oracle, and it can evaluate it for an input by making queries. Well, but we cannot look inside. And we need to decide whether it is constant or balanced. So first of all, let's talk about the oracle model of computation. There was a very famous real-life oracle of Delphi, where people used to go to her for advice. The difference with the quantum one is that the Delphi one was very cryptic in her answers, and we have a very nice oracle, and she gives us just the proper answers. But well, there's a catch. First of all, each consultation with her, each query costs us a little bit, like some amount of money. I'm saying this because this can simulate the computational cost. And what we can ask her is, in this case, what is f of 0? So this is a query for evaluating our function. We don't know what the function is. And she will just tell us it's 0, or she will tell us it's 1. So yes, well, how many times do we have to go to the oracle in the classical model to know whether our function is constant or balanced? You can write the answer in chat. All right, well, it should in the general sense. Here, remember that we have a very easy version of just being 0 and 1, just two options. So we do have to, for n inputs, here we have to put two queries in the classical sense. We'll see that in the quantum sense, we can get just one. So let's do it in the quantum way. So first of all, we'll conduct this. This is like a black box operation. So for designing the general circuit, we don't worry what it is. We can design it later, but we can just say that it does what we wanted to do somehow. And this is also how the oracle functions. That's pretty much the same. So the classical logical function f can be converted to a unitary operator, UF, when we construct a logical quantum circuit. So this is a circuit that allows us to evaluate UF only once. So we're immediately given the algorithm. So we are constructing a 2-qubit circuit, setting the initial states are 0. We want the second qubit to be in state minus. For that, we need to apply the X gate and the H gate. And to the first qubit, we only apply the H gate. Then we perform the unitary operation, put the Hadamard to the first qubit, and then measure the F qubit. And notice that we only measure the first qubit. We don't really care about the first qubit from now on. So when we measure it, if it is 0, then it will be constant. If it is 1, it will be balanced. So we will implement it later in this notebook, but first let's see why that works. The initial state, we have both in zeros. These, by the way, those are states in between. They will be helpful for calculating what the state of the composite system is at a specific moment. So we start with 0, 0. Then we apply an X gate. So you get 0, 1. Then we're applying the Hadamard to both qubits. So the first one will be in the state plus, the second one in minus. If we write out the state plus, then we can see that, well, multiplying it, this is what we get. Of course, this is the first qubit, this is the second qubit. Next, so we've already calculated psi 2. Now let's see what happens when we have psi 3. So we're applying the operator UF, unitary operator. Then we can apply it to both, just do the normal calculations with the operators. Next, we're using the special way of writing things from the phase kickback notebooks, where here will be -1 to F0, and then R0 and R minus. And here, for the phase, we'll have -1 to the power of F of 1. If we put the minus in front of the parentheses, this is what we get. And here, if you want to practice for the quizzes, which the quizzes are more theoretical, the assignments will be more practical where you write code. But my question to you would be to calculate all possibilities. So all of the possible F0s and F1s. We have seen examples here. There's only 4, so it's not that bad. Check the resulting states. And then my question to you would be to look at the states and see whether by this point you can tell me whether the function is constant or balanced, just by using measurement. So I will not have us do it now, but I will just excuse you for half a minute. I am back, and we will not be doing this right now. I think it's fairly easy to calculate, but calculations like these might be required from you during the quizzes. So I am considering this another extra task. All right, and the answer would be yes or no, and why. But let's continue. So we're applying UF to psi 2 and we're obtaining psi 3. That's what we calculated here. I'm just pasting it here so that we have a reference. Now we can focus on the first qubit, and just to make it easier on us, so the first qubit without the minus, we can write it in a different way. So in a just vector notation, we can take the 1 divided by the square root of 2 in front, and then just use the phases here. So the -1 to f of 0 and to f of 1 here. Next, we're applying the Hadamard gate to the first qubit. And so, well, this is the Hadamard gate. Applying it to the first qubit. What we'll get is, first of all, you can multiply this. So you get minus, you just get a half in front. And then if you just multiply it, so we will have 1, 2, 1, 1, 1, -1. Multiply it with -1 f of 0, -1 f of 1. So this is what we get after the just regular multiplication. So we have plus for the 0 state and minus for the 1 state. Now we have two cases. Either f is constant, and in this case, as we know from the definition of it being constant, f of 0 is equal f of 1. And so then we can calculate the state to be, they're the same. So you can just put f of 0 everywhere. So here it will just get 2 of this element, but because it's 2, we can bring it forward and this will cancel out to 1. And this will just result in being 0 since it's the same. We're subtracting the same thing from the same thing. And so the corresponding quantum state will be the -1 f of 0, 0. The 1 here is just 0, so we don't have to include it. And so we're observing 0 at probability 1. Next, if f is balanced, f of 0 is not f equal to 1, we'll get the opposite. So here you can just assign 0 to 1, 1 to another, and see how it cancels out. And because of that, here we're getting 0, and here we're getting the similar element. And the quantum state will be again -1 f of 0. This can equivalently be f to 1. If we, of course, put f of 1 here. And then we observe 1 with probability 1. We really like when this happens in quantum algorithms, because this means it will not be probabilistic, but more deterministic. So this means that with 100% certainty, we are able to say whether the function is constant or balanced, which solves our problem. Yeah, so this will be, let's mark this extra task as star. And this would be the clue to it. It's not the same, I'm just saying that it's something that can be useful. And this will be the last thing we do today. So we just want to implement Deutsch's algorithm. So we are given an oracle, and remember to run this cell. It will return randomly a quantum circuit with 2 qubits. So it will be, we are just given a function, we don't know what it is, either constant or balanced. And the circuit then will represent the operator the unitary operator, and 0 is the input, and 1 is the output qubit. All right, we want to implement Deutsch's algorithm. This is something for you to think about. And yes, you need to run the cell first to get the oracle. And then what you can do is compose, use the function compose, which is also very useful. You can use it with other gates. With functions. Oracle, and we just want to do it in place without assigning a name to it. And the barriers. The barriers are just something visual. So this could be seen as the barriers. It can help visualize stuff in our solution. We will use this. Okay, so finally, it's task 1. We have 5 minutes. And we're back. So time to implement our algorithm. Let's see. Oh, finally we have a name without the ones. So all should be good. Mm. Mm. Let's first we'll find the X gate unit 1. Applying the Haldeman gate to qubit 0. Applying the oracle. Just applying H to qubit 1. Gate H. And finally measuring. All right, and finally we'll draw a circuit. Let's see. Of course I didn't run the first thing here. And now we have the correct answer. This is not showing up because, well, we're using the composition here. Yeah, okay. And we're measuring only the first qubit. Is oracle returned from oracle.php? Yes, yes, it's from the other file that's in the folder that you have. So this is the function. Realistically, you can implement the oracles yourself, and we will be doing this. But the reason why we do the black box thing at all is because the oracle will be designed differently for different algorithms and different needs. But yes, this is similar to what we expected. And in this case, we have 0, which if we see here, we observe 0 with probability 1. So f is constant. Let's see if we got a different result. And we have 1. All right. I hope you got a similar result. Oh, now we have now we're shown what is being done in the unitary operator. That's good. We are left with one task which we are not going to be doing today. Because it's very, I would say it's very simple because you just want to do all the 4 functions that are possible and then try to see whether you need to apply like the X gates, for example, or what do you need to apply. So we want to identify the functions and we want to construct this circuit. I think it's a nice way to practice it, but not much more is needed. So basically, well, very often, just to sum up, very often in quantum algorithms, we want to see some sort of advantage. Why would we do all those things with like very complicated computers that are very vulnerable to noise, instead of just using a classical computer? So we want to find something, a problem, which would, where its solution would be easier in some way or better than the classical counterpart. And as you can see, it's kind of backwards reasoning that's very often seen in quantum computing, where first you just think of a solution. Oh, we can apply this neat trick. Like, we have phase kickback. How can we apply it to show some sort of advantage? And then Deutsch thought of a problem for it. So in this case, we are making only one query instead of two, and with 100% certainty. The problem with it being that in this case, if we're going to our oracle, since we just have two options, like 0 and 1, we just need to pay her twice, which is some sort of improvement, but it's much different than if we had to pay her 2n times. So that's just like a sort of teaser for what will come tomorrow. Yes, and we'll show some algorithms where, well, we'll save more money if we use the quantum case. Are there any questions? If not, then first, I think what is most important is showing how the homework will work. What you can see here is I am in student's view because I have a different role assigned. But this is essentially what you will see. In the homepage, you have basically the rules, and I advise you to read it carefully if you can. So those rules were already set. This is only mandatory if you want to receive a certificate. If not, you can treat it just as practice or not doing it at all. All right, and you'll see modules here. For example, this is available already, so you can do the quiz and the assignment. All the assignments and the quizzes, their deadline is October 18th. You can see how important, let's say, a quiz or assignment is based on the number of points they have. So, and here it shows what amount of points you need to get, so 50%. They will become open after we do each of the days. Assignments are programming exercises that will be graded automatically. So if there's some sort of problem with what you're doing and you think your solution is correct, but it doesn't give you the points, then you can write directly to our mentors, DM them, and please don't post your full solutions to the homework channel. Grades, you will be able to see your grades here. For example, I did one assignment here. I can see my score out of the possible score and the total amount of points. All right. Of course, if there are any questions, for well, Canvas here, you can ask them. So thank you very much for everyone who remained, but of course the recordings will be left. They will be published, so it's all right. And today is a special day in the fact that we went over time. So I did this thing that I wanted to do, and now, well, I thank you very much for today. The extra part that I want to do is just make a note together, because I feel like there might be questions about what our computation is with our qubits. So let's see again. Back to here. All right. So first, the operations that we have. I think it might be confusing and it's not really posted anywhere. So that's why I will include it. So first, I already showed you what the brass and the cats are, but let's say we have psi, which is alpha 0, plus beta 1, and phi, gamma 0, delta 1. Now, we can do some sorts of calculations with them. First of all, we have, those are cats, and we can also have brass. All right, so we can combine them in a few different ways. First of all, what if we combine it like this? Okay, and customarily, we write just one bar here, as if joining them. Why are we joining them like this? Because it's the inner product. Now, what if we connect them like this? Well, here, based on notation, you can see they will not connect. This is the outer product. And here, why I'm not telling you what it is exactly is because you can calculate it based on what the brass and cat is and see for yourself how it will be worked out. But just remember that you can usually just see by simple calculations. Another one. This we have been using today a lot. You can also write it and like this together. And this is called the tensor product. And finally, we have another possibility. This. And that's not a thing. This is an invalid operation. Why? Well, you can see it by the dimensions of the vectors if you take the vectors which is not defined. So this is what that will be. And finally, let's head to entanglement. What we're working in general, if you want to understand it more in depth, those are Hilbert spaces, which essentially is a vector space equipped with an inner product. So let's say we have two of spaces, like space H, A, and HB. This is the tensor product, so the outer product. And let's say that inside those spaces, we're building systems. System A and system B. Those are quantum systems. Those are Hilbert spaces. And finally, the quantum systems can have states assigned to them. So let's say I and phi B. Those are the states. And here we are also using the tensor product. The tensor product is nice because it shows us that we have two separate entities that are somehow joined together. And the way we call this thing, this specific thing, we call it a composite system. You saw it a few times today. All right, and that's what I wanted to say during the lecture. So if there are any questions to that, I can still answer them. And if there are no questions, then I will end the recording. And thank you very much for today again. I hope there were some things here that you found interesting. If you have any questions, even just like curiosities, then please ask them on Discord. I'm always happy to answer. Yes, tensor product. XOR. I think that's a bit confusing since the tensor product is something, I would say, more than just an XOR operation, but they do have the similar signs. Okay, then I will end the recording. Thank you.